before we work on worksheet problem 4a, which involve the statically indeterminate structure, we want to discuss the two concepts that are very important to solve with that type of problem. And the concept that we are talking here is compatibility and consistency. So let's start with compatibility. So what is compatibility? What is compatibility? So basically, when we have the structure that you cannot use the equation of equilibrium to solve for all the unknowns reactions, and that type of structure we call it statically indeterminate structure. And in that case, we have to go beyond equilibrium equation in engineering mechanics to solve. And to have that, we need to learn the concept of compatibility study. And with that, I want to demonstrate with the video, and we can go back to the lesson in a few minutes. This video to show the compatibility concept when we solve a problem that involves statistically indeterminate structure. What is a structure that is statistically indeterminate, that the number of equations that you use to solve number of equilibrium equation is not sufficient to solve for the unknowns, which is reaction, etc. So let me give that here. If we have a brown bar here, and if I have that support, and as you can see cannot move up or down, but I can rotate, and that can consider a pin. So two unknowns with one body in 2D, of course you can solve for that. Now what if we introduce more unknowns? Now two rubber bands, blue and yellow, are added into the structure. So with that brown steel member here, you have a pin, so you have two unknowns, and if you isolate the blue rubber band, you have another unknown. The force go vertically, and if you remove the yellow rubber band, you have another unknown with the force go vertically. So 1, 2, 3, 4. So 4 unknowns. So with that 4 unknowns in statics, if we use the equilibrium equation to solve, with the 2D we have 3 equilibrium equation, and the maximum of the number of unknowns that you can solve is 3. And here is 4 unknowns. So basically we cannot solve with only our learning in engineering mechanics. And the structure like this body that have the number of unknowns more than the number of equilibrium equation, and that we can say that it is a statically indeterminate structure. So with the statically indeterminate structure, we cannot solve with the equilibrium equation alone that we learn in engineering mechanics. And as you also know, in engineering mechanics, to solve for the more unknowns, which is the number of equations just less than the number of unknowns, you need to draw additional diagram. In this case, there is only one body here, so you cannot draw additional free body diagram. So for mechanics of material, we draw another problem that we call it compatibility diagram. So what is compatibility when I say incompatibility diagram? Compatibility diagrams is the requirement that after a structure has deformed, all of its deformation are geometrically possible. So there can be no gaps or no overlap. What do I mean? It's geometrical possible. Now, if I apply a load on one end of this steel member, and as you can see, in terms of the deformation, this steel is very hard compared to the rubber material. So you apply, you can assume the steel bar is hard, rigid. compared to the rubber band. And you can see the rubber band is deformed going down. So both are in tension. Both are in tension and it deforming. So when we say geometrically possible, and you can see the deformation for the blue rubber band and the yellow rubber band have to be go hand in hand. What does that mean? It have the geometry with the small triangle here and the big triangle have to be similar. So there is proportional between the additional deformation on the rubber band with the deformation on the yellow rubber band. And as you can see, if it's compatible here, so for deformation, there is no gap. That deformation on the rubber band have to be smaller than the yellow band. You can see there. And that have proportional the equation I'm going to write down in a few minutes. And you will use that concept to solve for other statically indeterminate structure problems. So draw compatibility diagram and draw additional equation from the compatibility diagram, which is use the similarity of the triangles, etc. in geometry. And now you have equation, another equation in compatibility diagram, and you use that with the equilibrium equation, which is from free body diagram. But they have to be consistent. So you need to have a consistency check before you continue to solve the equation from equilibrium equation from free body diagram and the equation from compatibility diagram simultaneously. So what does consistency mean in this case? So they have to be what you assume in free body diagram have to be the same as your assumption in compatibility diagram. So for example, this case, if I apply the load going down, both are in tension. So you need to see that the tension, and when it's tension, what does that mean? The deformation are increasing. The length of rubber band, blue and yellow, are increasing. So that have to be consistent. So if it's compression, then the deformation have to be reduced. It will be negative. It means the change, the length of the rubber band and the yellow band have to reduce. So in that case, as you can see here, it's in tension and the deformation is positive. It means it's increasing the length compared to the original length of these two rubber. So with that in mind, let's go to Rice equation compatibility, and we can apply for the problem today. So from that demonstration, you can see what I mean compatibility and consistency. And now let's take some note here. So compatibility, as you can see, is the requirement that after a structure has deformed, all of its deformation are geometrically possible. In other words, there can be no gaps or overlap. So let me make the definition here before we continue. That is the deformation without gaps. So it means that it needs to be geometrically possible. So with that, we have to draw the compatibility diagram. So let me model the problem that we solve in the demonstration with the member, the brown member. Now let me put that in a plug here, and then we have a pin support at one end, pin here, so it's not changing, and we have two bar. So the first is that is blue rubber band, and you can see that. And then we also have a yellow rubber band. So it's yellow rubber band. It here, yellow rubber band. And then with my hand, I apply a load P in there. So let me call the different point from that demonstration. We have, let's call that A, we have that B, call that B, C, and my load and my hand, my finger at P, apply the load P in there. So with that, as you can see, the rubber band is very flexible compared to the horizontal steel, and that we can assume ABCD, that horizontal member is very hard. So it's considered the richest. And then when we apply the load P, you can see that the member ABCD, it will tend to deflect, tend to going down, and the gap at point B here, we can see that the change for this point is delta B, that the deformation of the blue rubber band in the demonstration, and that point C, now it go to there, so that it will be delta C. Let's see, delta C. Delta C. So from that, we can draw the compatibility diagram. So with that, I can redraw the compatibility diagram. Diagram. And in compatibility diagram, we call that is CD. So it's CD in this class is not a compact disc. And as a matter of fact, no one use compact disc anymore, right? With many kind of electrical devices. So with the diagram, you can see I can draw the ABCD, original ABCD, and let's assume the distance here for that my models is about 12 inches, and I hang here is 7 inches, 3 inches, and this 2 inches. So that's what we had in the model that I demonstrated to you with that video previously. And then that diagram, it will be this member horizontal will be the leg down, go here, and we have delta B, and we have delta C, and from that we can have, because this point is fixed, this point is a support pin A, right? Support pin A, so we can A, it's not changing the vertical elevation because that is a pin. So you have B and C and D, B and C and D. So from that, with that dimension, we have here the whole thing is 12 inch, 12, and go there, it's 7 inches, 3 inches, and 2 inches, 2 inches. So from that, with that, we can assume with the small deflection, if we assume small deflection, and which is a reasonable assumption when we do in engineering structure, because you know, if it too much deflection or things like that is will you don't want to get into that type of building or structure. So with that, we can have with the make the geometrically correct or geometrically possible. Then from that we can have delta B. We can have delta B over 7 inches to make it possible. So we have a similar triangle, right? A, B, B apostrophe, A, C, C apostrophe. It have to be similar triangles. So we can have that equal to delta C over 10 inches. And if we have another point, for example, if we want the point D going down here, D apostrophe, then if we want to find out what actually the delta D here, what is the deflection at point D, then it equals to delta D over 12 inches. So with that, that basically the an equation that you have from the compatibility diagram. So because you need extra equation, otherwise for the statistically indeterminate structure, for example this one, you have a y, you have ax, and if you break it down, remember the rubber band blue rubber band, you also have another unknowns here, and you also have another unknown if you remove the yellow rubber band. So you have 4 unknowns, and that type of structure we call it the 4 unknowns. And in 2D equilibrium we only have 3 equilibrium equations, so that we call that a statically indeterminate structure. Statically indeterminate. So basically you cannot solve the problem with statics, indeterminate structure. Regardless, we have to still be able to solve this problem, and we have still be able to draw the free body diagram that you have. But to draw the free body diagram, you have to check the consistencies. So check the consistency that the other component that I mentioned in the demonstration that you watched previously. So consistency is very important. Check consistency. What consistency we have? So now with the statically indeterminate structure, we have to draw both diagram. The first, the free body diagram, and then we also draw the CD compatibility diagram that we showed there. So these two have to be consistent. So what do I mean when I say consistency? So for example here you say point B moved out, right? Point example there, point B move down due to my load. Then what do I say? That you have the blue rod, right? The blue rubber band. That I see that here have to be in tension. So that from your diagram, free body diagram, instead of you just assume compression or assume the tension, with that you need to put the correctly from your free body diagram that if you isolate point B, isolate the blue rubber band at point B, then you have to replace with the force that create tension in that rubber band. And similarly, you can see also point C also moved out, right? So from that, we also have to be the yellow rubber band in tension. tension. So in tension or in compression, you have to check what should be the behavior of that, so that we can use the equation from free body diagram, equilibrium equation, and you use the equation here for compatibility diagram from compatibility diagram, so that you can show them simultaneously. So what if it's not consistency, then you have to change the free body diagram to make it exactly behavior that you have. So let me make a note here. If free body diagram and compatibility diagram not consistent, so you have to change your free body diagram. Change free body diagram. So in other words, as you can see, make sure you draw the free body diagram correctly instead of just assume direction in there. So with that information, we can go to show the problem for A now.